Hey guys, today's video is about cross-validation. If you have watched my previous videos about cross-validation, I'm sorry that's not comprehensive, but the basic idea is not wrong. I just want to make this new video and clarify some concepts. To begin with, we use cross-validation for two purposes. The first one is comparing different algorithms. The second one is comparing different hyperparameters of the same algorithm. To be more specific, hyperparameters are external parameters that have to be defined manually and will not change during the training phase. How do we select the appropriate hyperparameters? Yes, we can use cross-validation. For example, decision tree is an algorithm and it has a lot of hyperparameters, such as maximum tree depth and splitting criterion. To select a better combination of hyperparameters, we basically run a cross-validation on each combination and select the one with the best performance. Another example of algorithm is k-nearest neighbor. It has hyperparameters like number of neighbors and distance measure. You can use Manhattan distance, Euclidean distance, or Minkowski distance of higher order. To be more concrete, cross-validation in model selection compares the generalized performance of multiple algorithms and select the one with the least error. Cross-validation is a more robust method than holdout method, since it estimates an overall performance of a model, which we'll demonstrate later. Further, least error essentially means the highest accuracy. As you might know, accuracy is not always reliable, especially in the imbalanced dataset. So, although we pick the model with highest accuracy, we actually have a lot more concerns in the real world. One thing to note is that the hyperparameters here are fixed. When we compare different algorithms, we have to assign a set of hyperparameters to them, and they are fixed during comparison. Actually, there is a method called nested cross-validation. It can do model selection and hyperparameter tuning at the same time, but that's a little bit complex, so we'll discuss them separately in this video. Next, cross-validation in hyperparameter selection compares the generalized performance of a single algorithm and select the one with the least error. It's quite similar to before, except we now only have one candidate algorithm and multiple candidate hyperparameters. Now let's go through the process of cross-validation. We'll use k-fold cross-validation as an example since it's popular, but other cross-validation methods have similar workflow, so don't worry about them. The first thing we do is splitting data into training and testing. Typically, training data is 80% of total data, testing data is 20%, but you can decide how to split your dataset. Importantly, only training set is used in cross-validation. It's because testing sets should not be used in the training phase. Otherwise, the model could learn the distribution of the testing sets beforehand, and the model performance evaluation will not be reliable. So, the next step is to do cross-validation. Since we are using 5-fold cross-validation, we split our data into 5 subsets of equal size. Remember, we only use training sets. It's only 80% of our total data. Then we do the same split 5 times since we are using 5-fold cross-validation. So if you are using 10-fold cross-validation, you have to do the same split 10 times. Okay, the idea is we use one subset as validation set, and the subset we use is different in each fold, and all the remaining subsets are used as training sets. So you can see the validation sets are not overlapped, but the training sets overlap with one another. Actually, the reason why we use cross-validation is to reduce the randomness in the split. By doing so, every time we have different training and testing sets, we don't need to worry about whether a particular split is better, because eventually we'll take average of them. How to do this exactly? we train the same model on the training set of each fold, and we evaluate the performance of model on validation sets. We repeat the process 5 times since we have 5 folds. Therefore, we have 5 accuracies after completing the training and validation process. Finally, our estimate accuracy of a model is the average of all the accuracies. In fact, each algorithm or each hyperparameter set will have an estimated accuracy. We just need to compare them and select the one with the highest estimated accuracy. But that's not the end of the story. Now we pick the best algorithm or the best hyperparameters and their estimated accuracy, but we still not have the final accuracy. Remember, our testing set is never used? It's actually used in this stage for final model evaluation. Another question is which model should we choose? When doing 5-fold cross-validation, we trained 5 models on different training sets. Should we choose one of them? No, we don't. We retrain a model on the whole training set. This includes both the training and validation sets because validation set is just derived from the training set, and a model can learn better given more training data. After we train this model, we evaluate the model's performance on the testing set. And here we are. It's the final model performance measure we present in the report. We don't use the average accuracy in the cross-validation, because that's the performance measure of 5 models. Alright, that's the workflow and uses of cross-validation. Hope you enjoyed this video and see you next time.